Hello, today I'm going to be teaching you about LRAM, RRAM, and MRAM. LRAM, RRAM, and MRAM respectively stand for left, right, or midpoint rectangle approximation method, and each method is used to find the area between a function and the x-axis. Each method is a Riemann sum, that is, you need to break the interval into subintervals for each method. Now we know that sometimes the simplest way to solve a problem is to do it geometrically. For instance, if we want to know the total distance traveled by the car in this graph between times 1 and 3, then all we need to do is find the area of the box made by the function and the x-axis between times 1 and 3. So the base of the box, 2, times the height, 50, equals 100, and we know that the total distance traveled by the car is 100 miles. However, sometimes you end up with graphs like these, where, for instance, the speed of the car isn't constant the whole way through. And unfortunately, it's not so easy to take the area of the graph like it is when you just have a simple little box. The solution? Simply start filling up the graph with a bunch of little rectangles and then take the areas of those. This is where LRAM, RRAM, and MRAM come into play. Let's start with LRAM. Now the first thing we need to do is create n number of equal subintervals. Let's say we're going to do 4 subintervals, each with a width of 2. Now LRAM uses the x value on the left side of each subinterval to determine the height of each rectangle. So for each subinterval, we're going to start on the left side of the rectangle, move up to the line, and then create the rectangle from there. You'll end up with something that looks like this. From here, the total area is approximated by adding the area of all of the rectangles. In this case, your answer would be 28. It is important to note that this is just an approximation. You're not going to get the exact area from using LRAM, RRAM, or MRAM. In the case of LRAM, you can note that whenever the graph is descending, you get an over approximation. You can see this by the way the rectangles stick over the function. And when the graph is ascending, you get an under approximation, which you can tell by the gaps between the rectangles and the function. The way to minimize over approximations and under approximations when using LRAM, RRAM, and MRAM is to make as many rectangles as possible. The more rectangles you have, the more accurate your approximation is going to be. Now let's take a look at RRAM. Notice that in this case it is the right side of each rectangle that touches the line. This is because RRAM uses the x value on the right side of each subinterval to determine the height of each rectangle. Now just like with LRAM, the total area is approximated by adding the areas of all the rectangles. In this case, the answer would be 42, considerably higher than the answer we got when using LRAM, even though it is roughly the same graph and we use the same number of subintervals. This shows why you need to be careful when using the approximation methods. Another important note about RRAM is that when the graph is decreasing, you get an under approximation, and when it is increasing, you get an over approximation, the exact opposite of the case when using LRAM. Lastly, we'll look at MRAM. In MRAM, you can see that it is the midpoint of each subinterval that reaches the line. This is because MRAM uses the x value in the middle of each subinterval to determine the height of each rectangle. In this case, once you add up the areas of all the rectangles, your answer should be 27.5. Now, because MRAM uses the midpoint of each subinterval, it is much less dramatic with its over and under approximations, and this is why MRAM is the most reliable and closest in its approximations of the areas of any given function. Now we'll take a quick look at how to solve a problem when we don't have a graph but only a table. Using this table, we'll use a midpoint Riemann sum with 5 subintervals to estimate the distance traveled by the hypothetical car in the first 10 seconds. The first thing we're going to do is split up the information we have into 5 subintervals, and we'll find the midpoint of each subinterval. Each subinterval and midpoint has been labeled so it'll be easy for you to see. Now remember, when we solved midpoint with a graph, we multiplied the height of each rectangle by the width of each subinterval. Here it's more or less the same. We have each midpoint labeled. Now we multiply it by the length of each subinterval, in this case 2. Here we multiply each midpoint by 2 as explained, and then just as before we add them all together for a total of 94, our total distance traveled. Now that we've done one problem together, try the next 4 on your own. Feel free to pause the video for as long as you want while solving the problems, and then in a few seconds the answers will be revealed. Here are the answers as promised. I hope LRAM, RRAM, and MRAM make more sense to you now, and good luck with the rest of your calculus journey.